It's really good. It's all good. It's good.
Hey, can people in the back hear me? All right. Welcome to CS 198 2026, Deep Learning for Visual Data. I want to thank all of you for coming to the first lecture and of hopefully 20 other lectures as well. I'm gonna introduce some of the logistics before Narasan takes over with the actual lecture content. And yeah, so this course is presented by Machine Learning at Berkeley, Lab, and we have an amazing team of people who, prepare all the course materials and are gonna sort of run this detail this fall. Not all of us could be here, unfortunately, but some of us are here. My name is Aryan. I'm a fourth year EECS major from Minnesota, and this is my second time teaching the course. Narsam's here, Rohan's also here. Yeah, and some of our other team members include Val, Verona, April, Derek, and Vanessa. Of course, we may not be here today, but you will see them in other lectures or them answering questions on EdSTEM or hosting homework parties, offsars, stuff like that. Just some quick things about logistics. Our syllabus is on the course website. For the interest of time, I'm not gonna go into that right now, but pretty much every detail you need is gonna be on there. Information about assignments, grading, the course outline, everything's up there. You should join our EdSTEM. This is our primary medium for course communication. This is where we will post all announcements, and this is also where you can, post any questions about the course content, about the homeworks, the assignments, etc., etc. Assignments will be submitted through Gradescope. So if you have not already joined our Gradescope, the code is right here. These lecture slides will also be up on the website after the lecture is over. So if you do miss it by any chance, you can also join both the EdSTEM and the Gradescope at a later time. Again, class is Monday, Wednesday, 7 to 8 p.m. in this room. Hopefully you know that by now since you're all already here.
Yes.
Office hours, location, and time is to be decided. We need to figure out, what rooms are going to be available. We'll talk to the department. I'll post a message on Ed about this once that is finalized. Enrollment codes were sent out earlier this week. Hopefully you have enrolled on Cal Central by now. If you have questions about enrollment, email us at dl4vd.epic23@ml.berkeley.edu. We will follow up with you on case-by-case basis. Yeah, as for attendance, we have not quite finalized an attendance policy yet. Regardless of what the policy ends up being, we are gonna excuse everyone from today's attendance because not everyone who wants to take the course has enrolled yet. We don't want to penalize them or anything. But yeah, once the attendance policy is finalized, we will put an update out on Ed. For now, just assume that attendance is going to be mandatory. Again, if you have any questions about course policies, make a private post on Ed or email us at the staff email. All of this information is on the website. But that said, I'm going to hand it over to Narasan for the first lecture.
Cool. Sorry, let me get adjusted real quick. All right, can everyone hear me? Cool. So let's jump into what this course is actually about. Computer vision. I feel like there are like three main subfields of machine learning, computer vision, reinforcement learning, NLP are kind of the hot topics. We're gonna go specifically into computer vision. It's like a broad subset of tools. There's like a lot of applications, classification, localization, object detection. Those are just like a few basic ones to name a few. We'll be covering those super in depth and trying to kind of speed run in order to get to what is the cutting edge today. So here's some like more popular applications. We have on the bottom right, we have like stable diffusion basically. I believe the prompt for this one was imagine a universe inside of a bowl of soup. That's like kind of crazy, and the math behind it is even cooler. And then we have on the bottom left, we have some 3D vision. So this goes even beyond like the top left where we see like classification and like uh, object detection, but like goes into the space of like, okay, can we take 2D images and then reconstruct what the 3D or real world object would have looked like? And then on the top right, we have a masked encoder decoder that can kind of help us with this like image generation. Um, let's backtrack a little bit because computer vision, for anyone that doesn't know, is like like a bit more complicated if you don't have some foundations in machine learning. So let's like talk about what that actually is. I think a good example is machine learning is also known as a universal function approximator. This is like a good paradigm to keep in mind because the goal of machine learning is to change the way that programming has worked in the past, where we just input in data and then output some like some product or like some feature, right? And now instead we're going to be taking in the input and the output and creating a function in order to predict our output. And so we're basically outputting a program now, and then we can take in unseen data and do predictions off of that. So why would we do ML versus like other programming? This is like kind of a hot take on machine learning. Is like, oh, like why do we even need this? Um, I feel like the best example is that humans are really bad at explaining what they want. They're also really bad at like trying to like look at high dimensional data and then take something useful out of it. Machine learning kind of solves that for us by just like black boxing the whole thing and then interpreting high dimensional data, and then giving us something useful, right? If you look at like a cat and try to write a program that can tell you if it's a cat or not using just if and else statements, that's going to be almost impossible. Um, and this is an example, right? So if we take like a very a classic Kaggle competition is like how high of accuracy can you get when predicting numbers? If you were to write from scratch how to predict the number 7, I can only imagine that as being just like some insane amount of for loops going over every single pixel. It's not going to be nice. Or we can write like 3 or 4 lines in PyTorch, which is a very popular machine learning language that we will be using. And those 3 lines will kind of like kind of solve everything for you. We're to try to like jump into the math behind those few lines. So yeah, like basically impossible to just like do this from scratch. And if you can't even predict a number, that like using just like traditional programming, how are you going to predict like how to form a full image or from scratch, or how to like generate a 3D model from scratch using just if and else statements? That's not going to work. So like, what is the right thing to do? Right, rather than just black boxing it, like let's start at something low level, right? I told you that machine learning is a universal function approximator, but what's like an example of a function that we could be making, right? So instead of trying to like go like pixel by pixel and trying to figure out like what matches to a number, what if we could just say this is a 7, it's unique from all the other images. And that's a lot easier because now we're writing a classifier rather than just like pixel by pixel detection. So here's an example of like that how that function might look like. We could just have some type of input, and we have like just some weight or parameter a, and based off of that parameter, we can determine like what whether or not it is 7, for instance. In this case, we're using red and blue. Based off of A, we're to determine whether or not like dots on a line are going to be red or blue. I think this is a better interpretation of what we're trying to say here. Is like if we have just these dots on a line, this is just like one-dimensional data, and then we're trying to like group all the red and blue dots together very simply. So rather than just saying like, oh, like storing all the locations in some type of hash mat and then referencing that or some dictionary, instead let's like create a function, what would that look like? Well, we have our parameter a, or our weight. We'll be referring to all parameters as weights in this class generally. They're pretty much interchangeable. We have our weight a, and then we want to know like what is a good number on this number line to like basically classify the red and blue data. And that like is pretty obviously one, right? It's right in the middle. Most of the red is on the left of it. Most of the blue is on the right. Um, and so like now we have our function, and that wasn't that bad, right? Like we basically just classified all that data without creating this complicated dictionary. And this made like a one-dimensional prediction way easier. And now like imagine what we can do at like a much higher dimensional space. Um, so here's like a 2D example. There's a few problems with what we had previously written. With just the like if we go back, our function is just predicting a single weight, which isn't super useful because, like I said, this is one-dimensional data. But there's a lot of data that was taken out when this was flattened into one dimension. If you spread it out into a second dimension, you realize that like, oh, just saying one and splitting the data down the middle isn't like super accurate. You're gonna have a lot of blue that's like on the bottom left-hand corner that is like not being classified appropriately. So in this instance, like we need a higher dimensional function or function approximator to learn. And so in this instance, it's like y equals mx plus b. We're going to be using linear regression. So now we're trying to predict two weights, m and v. And based off of those, we can split our data so that more of the red and blue are classified appropriately. Okay, so let's describe ML more like we kind of just like hand wavy said, okay, let's ML is a function. We're just gonna scale up. We saw one dimensional, we saw two dimensional. We're just increasing the number of parameters between the two dimensions. That's not like super helpful. Like you can't just scale infinitely. There's a lot more nuance, and let's jump into that. But before we jump into that, does anyone have any questions about just like the whole premise of ML, why it's important? Any definitions you're a little confused on? Okay. Feel free to ask questions. It's honestly really important. I feel like Berkeley just hammers it out of you to not ask questions, and that kind of like screwed me over for my like first freshman sophomore year. I learned by asking questions, and I'm sure you do too. So definitely feel free to ask any questions. Like no one like I know staff will not judge you. I can't say the same for your classmates, but I'm hopefully hopefully you guys are all kind. Okay, so let's jump into tax. Yeah.
Oh, I
Sorry.
was just wondering, to think, said we're just gonna have to five out. We like, other functions.
Yes. That is jumping ahead a little bit. But like not too much. But yeah, you can increase the dimensionality of your function approximator. But then we don't want to risk like overfitting, right? So if we, in this example, if we have like, okay, let's just say like circles are red and then X's are not red. And then we just have our data that's like more or less mixed. What we want to do is avoid overfitting and dimensionality. We also want to increase generalization. These are two terms we're to like jump into a little ahead, but I want to answer your question like fully, right? I don't know if everyone can see. It's not a great drawing, but if we increase the dimensionality of our function approximator enough, we'll get a line that like clearly wraps around all our data. So this is like a really good like classifier on the data we currently have. But when we're training, we don't train on, or like we don't train for the purpose of classifying the data we currently have perfectly. We train in order to get a function that approximates real world data into like a function of reality, or like something that represents the real world, right? And so like it is going to be a very high dimensional function. But then in the real world, we might in our test set, we might have data that's a little more mixed, and then suddenly our classifier is like completely wrong. This is why it's important to like maintain like you don't want like too high dimensional functions. You don't want too low dimensional. This is something that you have to like kind of fine tune when you're actually creating your model. Yeah, great question. And then also like as a brief side note, this kind of gets into the whole point of what we were saying before, like previous programming paradigms versus current programming paradigms. Before we have Newton saying like, oh, like here's a bunch of kinematic equations. You just take in data, put it into our formula, and then we get information about the real world. Now we're taking the information about the real world and the input that we got to get that data and then filling in the blank. We're literally solving for like kinematics basically. And you can do that. Like if this was data about like gravity or something, then like you could literally solve for like a basic approximator of what gravity is or yeah. Sorry, that was a little side note. Any more questions? Cool. So I briefly mentioned before that there's like three subfields of like three like hot topic subfields like CV, computer vision, NLP, natural language processing, and RL, reinforcement learning. But here's like even broader than that. Like those are just like hot topic Twitter type things. This is actually like more the accurate breakdown of what the three distinct fields are. We have supervised, which involves taking like label data. So in this instance, we have like an X and Y axis. If our X and Y axis are given to us, and we have information about like the coordinates, basically, that's going to be our labels. That would be supervised. If we didn't have a labeled X and Y axis, and we just have data that's kind of grouped up, that would be unsupervised. So we don't have any labels. Reinforcement learning, I like. It's pretty interesting. It's more like the cherry on top, right? You'll usually put it on top of the supervision or unsupervised models in order to like kind of like fine tune. These are more for like environmental interactions. Like if you're interested in robotics, you'll use reinforcement learning. Yeah, but we're going to be focusing on like kind of the computer vision part of these three subfields. So these are like vocab terms that are really important to pretty much all machine learning. You're going to see these pop up time and time again. So if you have any questions, like answer them now. I'll answer them now. You ask the question now. So we have our function and our model. These are interchangeable. Also, yeah, this lecture and slides will be posted as well. So our function, our model, we talked a lot about universal function approximators. We also talked about how parameters and weights are interchangeable. This is kind of like with our y equals mx plus b, our coefficient m and our b are kind of our weights that we're predicting. We tune these in order to like take our input x and create something useful. And then we have our hyperparameters. Our hyperparameters is going to be like what you were talking about like, oh, like how do we choose the dimensionality of our function that we're approximating? Or like more or less what is the size of our model, or like different things like learning rate that will come up later. This is the hyperparameters. These aren't directly tuned by the model itself, like weights, though you can have kind of like some auto ML features that will allow automated hyperparameter tuning. And then we have our loss or cost function. We haven't like gone too deep into that, but our loss function is basically like saying like how accurate is our prediction from our current data. So it like a common one is L1 or L2 loss, or like mean squared error. Those will come up in like data 100, 189. And then we have our feature. This refers to like the bits of the data. This is really important in like computer vision because within there's this thing called a CNN, a convolutional neural network. Our features are just kind of like, okay, well, if we have an image of a cat, an ear of a cat would be a feature. It's the job of the program to learn how to predict whether or not an ear is in a certain shape that's a cat. And then if it is, then like maybe increase the probability that this is a cat. Any questions on these definitions? Yeah.
I still don't understand what.
Yeah. Let's go back to like an image just for the visual part. So we can see like with this cat image, in order to detect that there's a cat in this object, like how do we distinguish the cat from the background, right? The way that we do this is by instead of just having like a line that will like like kind of surround it, like using linear regression where you just have like divide the red and blue dots. Instead, you'd have to do something like called a CNN, a convolutional neural network. And what that does, instead of dividing data into like red and blue dots, we instead slowly learn features. And so basically, like you're breaking down the image into like small distinguishable parts. And so like you might have the ear of the cat might be a feature that you learn over time. And then like as you go deeper and deeper into your model, your features start becoming, or theoretically, they start becoming more similar to the whole object itself. So if you get to like the final layers of the model, like a one or a zero, not really, but like a one or a zero, you can imagine might correspond to like, oh, this is a cat. And if you go like slightly earlier in the model, it might be like, oh, this is the body of a small animal. If you go even earlier, it's like, oh, these are ears, etc. So like, yeah, features are just kind of like learned parts of objects. Does that make sense?
So if you like.
Yeah, patterns in data. That makes sense.
Yeah, if I can jump in. Feature is basically any information that you can extract from an image, right? So if you have an image of a cat, some information that you can extract is, what kinds of edges are there? Can be horizontal edges or vertical edges, right? Or what kinds of colors are there? Like you have, a predominantly green or a predominantly red edge, right? So any information that can be extracted from your data. So if you're say working on something like predicting the price of a house, the feature can be how many rooms the house has, or whether it has a backyard or not, or the area of the house. So it's any information that you can extract from the data that you can input. That's just the word features.
Yeah, and that's a common Data 100 project is like a house cost prediction. And you see in that project that like, oh yeah, like not every feature has an equal weight in determining whether or not something is the correct price or whatnot, right? The square footage of a house has higher correspondence with the cost of a house than the number of faucets, right? So these are two unique features, but they have different weight in terms of whether or not they can correctly classify the objects. Sorry. Okay, so this is kind of like ML operations type things. We have to start by determining whether or not we can actually apply ML to the problem. Like basically, are we missing a function that we need to approximate? Or is it just like software that we need to write? And then we have to prepare the data. That's a huge one for computer vision. High quality data is hard to come by, and it directly determines more or less whether or not your whole model even works. And then you have define the model and the loss function. We briefly talked about both of those. And then you have to minimize your loss function or train the model. We're going to go into the more in depth on what that looks like in the next few slides. And then you're kind of done. Yeah, this is a very high level overview. Okay, let's jump into like what types of questions you need to be asking when defining the problem. You need to be asking like, what does your input look like? What is kind of the like for our like action space or feature space? For computer vision, where are we talking about like, okay, like how big is your image, right? Is it 64 by 64 bit, HD, 4K, da da da? And then also like we might want to do some data augmentation on that. Like how high quality is our data basically? And then we have what are we trying to do, supervised or unsupervised, and then metric level for success, what accuracy percentage are you going for? Okay, let's talk about data representation and preparation. This is super important in computer vision because we have to have high accurate data to predict things accordingly. What this also corresponds to is like we have to have appropriately labeled data as well. So usually when you're classifying for accuracy, the correctness of your labeling matters like more than your model itself to some degree. Like models can be interchangeable, but having poorly labeled data would completely destroy any model that you try to build. This is a little overlooked. This is also an issue with like ownership of like different images, etc. I'm sure you've seen some of these lawsuits in the news. And then like we briefly talked about, feature selection / scaling. So we might say like, okay, like the square footage of the house might be more important. That's a feature that we want to keep in it, or and so like we might want to scale that, increase the weight or importance of that feature. This is more like application specific. And then we have one of the more important takeaways from today's lecture, is that almost all your data is going to be stored in like vectors or matrices. So in this instance, with our red and blue dots, we're not going to be storing some type of graph. We're not going to be storing a plot. We're going to be storing the x and y coordinates as a vector. This is an example of this is just like a case study. We're gonna be talking about representing labels using one-hot encoding. So instead of saying cat or dog, because this is computer vision, we're not talking about like NLP. Our model does not understand what a cat or a dog is, but it does understand what like a 0 or 1 is. So usually when you're classifying like whatever your list of objects you're trying to classify, say we have 5 different animals, we'll just basically take a vector of length 5, and that's going to be our final output of your model. I guess I'll draw a big image. So basically, we'll take our 64 by 64-bit image, and then we'll like pass that through. More or less, you can imagine it right now as a black box, but also a massive funnel, which basically creates this vector. And that vector is going to be the classification of what percentage accuracy is it going to be for a cat versus dog, etc. So if we're passing an image of a cat, and the first position in our vector is a cat, then we might, our goal is it to be 1, 0, 0, 0. So that means like the first position is going to be the correct classification of a cat. This is one-hot encoding, the idea of taking objects and like basically assigning them to these like binary values inside of a vector. This is the goal, right? The absolute correct classification. What it might end up looking like is more of a percentage breakdown. So like if we have, say, the first 2 are cat and dog, and the last 2 cats, dog, and then our last 2 are just like 3 reptiles, let's say. So they look completely different. We might get numbers very close to 0 for these 3 values, and then maybe we say like 0.8 cat, 0.2 dog. So like this is maybe something more accurate, but the whole goal of like computer vision is how do we boost this number, the correct classification, as high as possible. Any questions on one-hot encoding or yeah? Cool. Okay, I briefly foreshadowed the whole idea of augmenting data. So what happens, for instance, if we have high quality data, but we don't have enough of it? So we can't correctly classify anything, especially since we briefly mentioned that like, we don't want to create a case of overfitting, which we'll go over more what overfitting means, but like we don't want to get a case of overfitting where we create a just narrow representation of like, this is the correct classification, this is the incorrect classification. This happens a lot when you have a small amount of data because you don't have like a lot of representations. Like if you have a lot of poodles, that might not be a good way to like measure if you can correctly detect a dog. It will be a good way of measuring if you can detect a poodle though. But what if we did some data augmentation to our poodle? So like what if we change the brightness of the poodle, or what if we we made the poodle smaller, or we cropped out half the image of the poodle, for instance, or we flipped it, etc., doing different transformations on the data, never changing the pixel values, for instance, but definitely changing like the pretty much everything else. And so this is a way to like increase the amount of data that you'll have in your like training set without like decreasing the quality of the labeling. This is really important when it comes to like more so like the pre-training. When you're dealing with basic classification, there's a lot of data out there. But when you're dealing with more nuanced classification or model generation, or whenever you have a time when you have limited number of high quality labelings, you're to be augmenting data. Partitioning data. So this is the idea that you never want to train on your tests. So in our example here, where we have circles and x's, right? What I mentioned was like if we create a high dimension function that perfectly separates the circles and the x's, that's going to be the data that's on the board. We want to be our training set. And then we also have a test set because we want to see if our function is actually accurate to the real world. The test set is meant to be a representation of like, oh, what data would you see in the real world? So it's not like you're going to be given tests and like a test set or a training set. You just divide the data that you have collected. Usually it breaks down to like 0.8, 0.2, or this number you can change to whatever. But say you have 80% of your data that you currently have is going to be partitioned to only train. So that's going to be the data that we have. And then our 0.2 is going to be our tests, and that's going to be a way of evaluating whether or not the data that like the classifier that we built is actually accurate to data that we might see in the real world. This is a way of just seeing like, oh, is our function like too high dimensional? Did it overfit? Basically just seeing like, did the function we create, is it useful in the real world? Is it an actual rule of data you'll see in the real world, or is it just like some like weird math that we did and like correctly categorized two different objects? Yeah, and another way of doing this, if you don't have a lot of data, say like even like 0.8 and 0.2, like that's just percentage. Say you only have like 60 images, and you want to save as much data as possible for training data. I mean, you can try to decrease this number. Let's say like make it a 0.1, 0.9 split. But say that's not enough. One thing you can introduce is this thing called k-fold cross-validation. And what that does is it will take this number of our training data, and instead of only doing our evaluation of whether or not our data is accurate at the end, we can instead further split our training data into multiple like subsets. And all these are basically the same. So this is our 0.9 that we took over here. And then we're going to split our 0.9 into 10 different parts. Pretend that there are 10 sections. And then we're going to take our first section, our 10%, and then we're going to make that a test set. So like a test set within our data. And then we're going to shift this test set down one. And we're going to do this k times. So just imagine there's a number of times. And we're shifting over the data that's our test. So we're never repeating what data we're actually testing on, but we're shifting around kind of what the data that's in the test. This is not a very good image. Does anyone have any questions where I can try to narrow down this explanation? The reason why I would use yeah.
One thing I was wondering is, you give examples of like when you're trying to classify a cat, what does it actually look for? Like, is it like pixel brightness or like the shape?
Yeah, so like this funnel is actually just a black box. As like the theory is that as you get farther down your funnel, you're gonna have things like, oh, like this is a cat's head, and then up here might be like this is a correct prediction of a ear versus a tail, da da da. And then like all the way at the top we might have Aryan mentioned like, oh, this is a line, right? Or this is a horizontal line. This is a like a reverse. And so like you combine a lot of these like smaller representations of like what a line or like a horizontal, vertical, and you combine all these small lines that you can recognize into more complicated features. Like this is literally just like two lines, at least the way that I drew it. And so then as you go down your funnel, you get like more and more complex features. But like when looking into the actual black box itself and trying to visualize, most of it literally is just super ambiguous. Most of it's unique to the model itself, because you're literally dealing with like data that's in a higher dimension than like humans really understand. But yeah, does that help?
It's like the
You will, all of you will, for your homeworks. But who initially made it, I don't know. But what this funnel actually is this thing called CNN. And the funnels might not be the best way of saying this. It's more of just like a slow culmination of different features that are layered on top of each other to get more accurate representations of objects. Yeah, and so like in PyTorch, literally what you do here is you do like NN or you'd import PyTorch, and then you do NN CNN or NN con, and then you'd pass in like the dimensions of your input and output. And there's a bunch of other junk. But the input and output is slightly relevant here because this is the number of like kind of feature representations you'll have. And so your input and output channels in the beginning it was like, oh, like your initial features are just going to be kind of lines, not super understandable, and then later on you'll get like more complex features. Yeah.
So, I just have a question about the testing side. So can you also do the data augmentation side, or you can do that?
You should actually do like whatever augmentations you apply, you should be to both. Yeah, it's like not super like your augmentations are transformations. Like in math, when you transform a matrix, it doesn't change the data in the matrix, right? This is the same thing here. Your data should never be like changed directly. The value shouldn't be modified other than scaling. So like literally, you should be able to go back to your original image using simply linear operations. As long as you can do that, you can apply your data augmentations to test or data train. Yeah, good question.
So are the weights in the neural network updated depending on how they pull on the validation data?
The update on the training data. Yeah, it's a good question. The update on the training data, and then on the test data is to see more whether or not you overfit on the training data. Yeah. Your test data is kept separately for the sole purpose of seeing if unseen data is correctly classified. Usually, you'll have a higher accuracy on your train versus your test. You also will never update what you're saying. You'll never update your weights based off of the test because you want to keep that test data as if it's unseen by the model. Because the only way to determine whether or not a model is a function that universally approximates is if it works correctly on unseen new data. Yeah. Any question? Okay. Cool. Good questions. I like this. Let's go into like the more nitty gritty, defining the model and our loss function. So we talked a lot about the different kinds of models. We talked kind of about linear regression. That's like a very basic model you might use for like housing prediction. You can also use logistic regression. But we want more, what we mentioned very briefly, is convolutional neural networks, or just neural nets in general. Our model, like the depth, the size, all the different parameters are basically have to be tuned to the complexity of the task. For classification, it's like fairly easy. You don't need like a gigantic network to classify images correctly. You also might not have enough compute for that. But like I said, the classification is just like, oh, cat versus dog. But generating an image from scratch by just a text prompt, that's definitely going to require something a lot larger because you can't just do that with linear regression. But sorry if that's a little hand wavy. Okay, let's also go into loss. We haven't really touched upon this at all yet. But the typical loss that you'll see is L1 or L2, which is mean absolute error or mean squared error. This formula you should be really familiar with, or like you don't need to be familiar with it now, but get to know it. So we have on our like kind of inside that like whole parentheses you have on your left side is yi. That's the observed versus predicted. The predicted is the y hats. And so like the difference between the two squared on average is going to be how off you are in your prediction. Does that make sense? I guess checking. I'll also rephrase it briefly. So like if we have if we have the predicted line And we say that this circle is actually an x. The difference between where the x should be and like where our predicted value actually is going to be like how off we are from the correct classification. So we'll shift like kind of our prediction over slightly based off of like how big our loss is. And there's this thing called a learning rate that will determine like basically how big should your like your change be based off of your loss. I think I kind of want to draw a better image than this, so let me redraw it. There's this fun thing I like doing when I'm kind of explaining how loss is adjusted is if we have our data points, our loss is kind of like our prediction is a line, right? We talked about linear regression. Our loss is going to be kind of the distance to this line because for this x, for instance, for this x, we incorrectly classified it using the line. So like our distance to the line is our predicted value, or whichever one it is. Doesn't really matter because it's squared. But like this is our loss in this vector. And then we want to like decrease the loss, so we might shift our line slightly, like one way or the other. And our learning rate is going to affect how quickly we move our loss, our predictions, basically. And so like the whole point of this analogy is that our loss function will determine more or less like how much this will swing back and forth, and then our learning rate will determine how slowly it swings. If we are oscillating too quickly, we might not reach like the optimal, right? We might oscillate back and forth like a pendulum. And if we don't oscillate fast enough, we might trade a local minimum where like, okay, right here is correctly classifying things, but there's like a bunch of data that's misclassified. But if we had a slightly higher or lower learning rate, we could get to like global optimal. Yes. That's determined using mean squared error or
like how are the states?
the distance between the
So like what would the
yeah, so good question. So like this line would represent kind of our prediction. So like but if it's like on the bottom side, it would represent a circle, top side would represent an X. So this is like binary classification. We're drawing the line here, everything below it is zero, everything above it is an X. The distance between the prediction line and our actual input observed data is going to be our yi is going to be the actual data. The y hat is going to be kind of the line. The distance between the two is how much loss we have. Our goal is to minimize loss, so we might tilt our line so that the distance between the observed and predicted is smaller. Yes.
so we wouldn't since above the line.
Well, you would include all the distances. I was just drawing it that sense.
So like correct data values classified correctly. It's like
Well, yeah, the loss function is computed over like all the data that you have. So like if you see I to n is the number of like data points that we have. And so this loss function is computed over all the data. For correctly classified data, yi minus y hat is going to be 0 because the predicted versus the observed did the same thing. That's 1 minus 1 is 0. So then the loss function wouldn't do anything in the case of a correct prediction, which is why like you want our loss function to like kind of go to 0 because that means that our predicted and the real thing is the same thing. Yes.
So you'll have a lot of like different loss functions, right?
Yes.
Just like your network wants to predict like CAS, so in this case you will have like you will only want that point to be 1 and all the other points to be 0. But when your network wants to predict a dog and you want the second point to be 1 and the other point to be 0, that means you will have a lot of different under like loss values in the end of the tree.
Your the loss function will go over like all the weights.
Yeah.
And the loss function itself is like this formula. So you're not gonna like have a bunch of different formulas that you'll end up with. But you'll end up with a lot of different weights that you'll
Yeah, I mean a lot of ways.
yeah. So like you will have like your network is full of like a lot of different weights. And all of them will be updated based off of like whether or not it was a correct classification. And so like the goal is that like, oh, if we do train it off of cats versus dogs, and then our loss function, if we update it enough with a loss function for both cats and dog classification, then the weights will directly classify or correctly classify both cat and dog. So like the network is shared, right? All the weights are shared. The loss function operates on both. Oh, wait, did that answer your question?
Yeah, also like what's the form of the weights in the end? It's like a matrix.
Yeah, it's like a matrix. It's called a tensor. It's just like massive, high dimensional. Yeah.
So I know that in machine learning, also accuracy function is that related to loss function.
Yeah. So like this is like kind of a bit of metric of accuracy, because we are trying to predict like how off are we from our observed versus our predicted. But in terms of like our actual prediction accuracy, usually what you'll have is inside of your training loop, you might have like another loop nested inside of it. And so like every say like 10 epochs, like an epoch is just like an update. So every 10 updates or so, we might say, okay, like let's run our actual model on this unseen data called our test set, and then say it correctly classified like 1 out of every 10, so 10% accuracy. And we know if it's the correct accuracy because our data comes with labels. And so like we use our ground truth label compared to the function, what the function says the label should be, and that's going to be our accuracy, and that's going to be nested inside our training loop. Yeah, good question. Cool. But yeah, loss functions are a huge deal. Yeah, they're like I'm glad you had so many questions. It's like one of the foundations. Okay, training the model, minimizing loss. So we found out that the model was a black box, kind of. We found out that loss is the difference between our predicted and our real. And then now we have to figure out how to minimize the difference in such a way that we reach a global minimum, which means like we have the highest accuracy for our data. This this is a very fast slide on training. But now we have our data, our model, our loss function. We have to apply different training procedures. This is going to be covered later on, but our training procedure is pretty much unique to which model that we have. For classification, it might look like we have our mean squared error, and then we have our optimizer. Yes.
Is every function we're trying to learn something?
So this is a good question. So mean squared error, I don't remember particularly which, like some loss functions can have multiple global minima. But usually they like based off the only reason they wouldn't have a global minima is if like your data like doesn't have enough features. But like your loss function graph, right, is mean squared error is going to be this. And so your global minima, like there is going to be one. Same thing with mean absolute error. You're going to have a global minima, but this is based off of like your one data point. So for one like data point for one classification, you will always have a global minima. But in terms of the entire network, you could theoretically have multiple. But I feel like that's more like a data question. But for like the actual formula itself, yes, there's always a global minimum. Whether or not you can arrive at that, that's a different question. Because I like to imagine it like a ball, right? If we have our loss and say we're right here, and we decide to update our loss by some amount, we can scale that amount by our learning rate. In our learning rate, you can imagine as kind of like what speed are we going at, and then the direction is like the loss, and together that makes velocity. And so the velocity that we're going at might be too great, and then you'll end up bouncing around to around your global minima. So in theory, you might never reach it, but that's not because of the formula. That's because you might have chosen a learning rate that makes your loss bounce around the global minima. Yeah. Any questions?
I just have a follow-up. What about if we're learning a function that may have local? Let me make sure that you don't end up staying in the local minimum rather than.
Yeah, it's a good question. So like there are a couple of ways of doing this. You're not gonna have like a single like 2D dimension. You're not like so your global minima is going to be like a lot more rare. You're gonna have a lot more minima. I can't really draw a 3D plane. I'll try to get an image for next lecture. But like short answer, you have to do a lot of fine tuning using learning rate, using increasing batch size to have like a more stable direction of loss, which means more data points. And then you can like tune which activation function or which optimizer you use. And then the last thing is weight initialization, which you don't know about yet, but we'll be talking about that later. We have a lot of slides. What time is it?
It's
Shoot.
Yeah. It's fine though. Lecture slides are posted on the website. Anything that you missed should be on there. I know that there's some stuff, like the generalization stuff, iceberg that's gonna appear on the first quiz. That's completely fine. These quizzes are supposed to reflect competition, not really correctness. We will have a limited sense of them. And of course, we will cover some of this in the next lecture too. And if you have questions about any of the topics that we get to, or any topics that we did cover today, you have office hours, we will post that in the Ed channel. So you can also post questions on the Ed forum. One of the staff members will reply.